Hi everyone, welcome back to the lab. Today we're diving into something I find very exciting, and that's transporting PCI Express over fiber. That's something I've had in the back of my mind for a little under a decade, but I've only really started toying with it on and off for the last year or so. My final end goal here is to have a remote box on my workbench behind me where I can host some PCIe cards and have those connected to my main workstation on the other side of the room, currently behind the camera. Just to be clear, this is not a new idea, and there are vendor demonstrations of such links using the specialized chips and optics. And there are also off-the-shelf commercial solutions you can buy for remote PCIe box using optical as a transport. But as far as I can tell, those ready-to-use solutions are not very common and still pretty expensive. Now, before anybody says anything, I do realize that nowadays active optical cables for Thunderbolt are a thing. When I first started researching this, I'm not sure they existed yet, and it's only recently that they came down in price to something reasonable. They're not cheap by any means, like still like 500 euro or so for like a 15-meter cable from a quick search. But if you want an off-the-shelf solution today, you can look into that. I'm not really considering them a good fit for me though, for a few reasons. First, it's Thunderbolt, which isn't PCI Express, it encapsulates PCI Express. That adds a layer of complexity I'd rather avoid, and it would also require conversion at both ends of the link. Plus, I want something connectorized at the optical level. I'm already transporting Ethernet and some other stuff over fiber in the lab, and I've got single mode fiber bundles running around, and I want to make use of those. And finally, perhaps most importantly, I want to go through the motion. This is a learning exercise to get my hands dirty with the lower levels of PCI Express and high-speed serial links. I originally had planned to make one big video showing the final product, but the deeper I go, the more I realize how much ground there is to cover, including a few side quests I didn't expect. So I've decided to take you along for the journey. I'll be posting updates as I hit major milestones, and this is the first one. Anyway, enough introduction. Let's get technical, shall we? My first idea was to be rather modest and only go for a Gen 2 by 1 link. But over time, I've revised that and I'm now aiming for a Gen 3 by 4 link. Mostly because that's what you can fit on cheap-ish optics. You can find QSFP 40 gig LR4 modules on eBay for less than 20 bucks. And they can do 4 10 gig links on one single mode fiber pair. They use wavelength multiplexing. So those should be a perfect fit to carry 4 Gen 3 lanes at 8 gigatransfer per second. As a side note, from now on, I'll always talk about SFP, but know that QSFP is pretty much just 4SFP in parallel. As you probably know, PCI Express is a high-speed serial link, so you have one diff pair for TX and one for RX, that for each lane. Similarly, SFP plus optics also have a high-speed serial link interface with one diff pair for TX and one for RX per channel. So you just wire those together and project done? Yes and no. There are a few possible complications, so let's go over those. I think it's also a good moment to point out a blog post by Eli Belower that first introduced me to the idea and goes over some of those potential problems. Link down in the description. First possible issue is the SFP modules themselves. Are they transparent to the data and can they work at a line rate that's different? Cheap modules are meant for 10 gig Ethernet, and that would be a 10.3125 gigabits line rate. And we want to carry PCIe, which will be 2.5, 5, or 8 gigatransfer per second. Thankfully, for 10 gig modules, that's mostly the case. They do simple on-off keying on the transmit side and amplify and slice on the RX side. No complex retiming or anything fancy like that. Now, if you're going for fancier or faster optics, those will start doing advanced processing, and that can be a problem. Personally, I've been using 10 gig LR modules from fs.com, and that worked fine. I've also tried their multimode 10 gig SR modules and had some success with them, but it seemed a bit more fussy. It's possible that the multimode has a bit more smearing, so stick to a single mode if possible. Second consideration is the electrical interface. Thankfully, we're mostly good there as well. The SFP Plus and PCIe data lanes are close enough and should interoperate just fine. Technically, the AC coupling caps and termination style will be out of spec for PCI Express, but that won't be much of an issue, except for one aspect, and that is receiver detection. And that's our first real trouble. PCI Express attempts to detect a link partner by using common mode pulses and relies on specific values for the coupling capacitor and a single-ended termination to achieve this. Both of those will be off for an SFP module. The PCIe transmitter won't see a valid link partner, and it will never even attempt to bring up the link. Third consideration is out-of-band communication. Some high-speed serial protocols like USB 3 and SATA use low-speed signals pattern on the data lines that are not purely differential. Those wouldn't go through an SFP module. Thankfully, PCI Express doesn't really have anything like that, so it's a non-issue. There are some low power states where PCIe shuts down the transmitter, but we can pretty much avoid those altogether by force disabling ASPM on that specific link. The fourth consideration is spread spectrum clocking, or SSC for short. To meet EMI emission standards, a lot of PCIe hosts will modulate their clock by a small amount, around 5000 ppm. In a classic PCI Express system, the device will get its reference clock from the host in parallel to the data lanes. And that reference clock will also follow the same modulation so that the device can stay in sync. In our case, we're only sending the data lanes through the SFP, not the reference clock. And as such, SSC will be our second real trouble. The final consideration is specific to Gen 3, and that is link equalization training. Because of the increased data rate, Gen 3 introduced a specific training phase during the link initialization where the partners negotiate pre-shoot and de-emphasis parameters from each other. Unfortunately for us, the electrical to electrical conversion of going over SFP modules will break that feedback loop and make this step fail. That's our third obstacle that we'll need to work around. So, in summary, to get a PCIe link over SFP optics, the three things we need to work around are receiver detection, SSC clocking, and for Gen 3 only, equalization trading. Spoiler alert, it's possible to get around all three, often in several ways, and I'll go over them in due time, but for now, I think it's enough theory. Let's go to the bench, and I will show off the first setup I used to get a basic link up and running, and then maybe a small side quest. Okay, so we're at the bench now. This is the test setup we're gonna work with. This is a Raspberry Pi 5, and I have for it a PCIe breakout box, which basically takes the PCIe flex that the Raspberry Pi 5 has and gives me a real PCI Express slot. This will be our PCIe host. This is a Blackmagic Decklink capture card. I'm just using this as a test PCIe device, basically. That's just our target device, just something I had laying around. And the advantage of that card is that it's also supported by Lytix, so it has an FPGA on board that you can actually reprogram, and so you can actually load a custom bit stream on it in case you want to debug some PCIe stuff. It can give you some low-level access. We're not gonna need this today, but I'm just mentioning it for the future. And also, if you're looking for a cheap Xilinx card, this is actually pretty good. These two cards, they're actually the same card, and they're a custom card that I designed to do these experiments of carrying PCI Express over fiber. So obviously both are loaded with an SFP module. This is just modules from fs.com, 10 gig LR. And then between them, I have, I think it's like 2 meter or something of single mode fiber. I've actually tested with longer length. It doesn't really affect anything, so that's not a problem. This is just what I had laying around. So let's look at this module in more detail. So one thing you can see, obviously, this module. I mean, I've currently have it out like that. For the experiment, we'll have it plugged in the Raspberry Pi 5. I just have it here, so I can point at stuff. Obviously, we have the optical module here, and then here, I don't know if you can see, but there's a little chip, and that's a redriver. And so that's basically going to take the signal and repeat it, and optionally apply some de-emphasis or equalization of some configurable things to redrive the signal as we want to. And here there's another chip which is just analog switch, gigabits mux basically, and it allows me to either connect the PCIe slot to the optical module or connect. Here I have a USB 3 connector that I can connect to the module instead. Now, this is not used for USB 3 at all. This is used for this thing here. And that's because, in the miner, the crypto miner community or something, they've taken the habit of running PCI Express over a cheap cable, and especially cheap USB 3 cable, and reusing USB connector. And so I'm just using this to connect to this board, which is just a breakout, taking the signal from there to a PCIe slot that I can just connect to this board. Honestly, it's not a great solution. It works okay for like Gen 2, but if you try to go to Gen 3, even just the breakout and the cable itself can create too much noise and too much signal degradation to Gen 3 to have Gen 3 work by itself. So it's not a great solution, but in this particular example, we're gonna limit ourselves to Gen 1 and Gen 2. Let's have a quick look in KiCad at the design of this board in more detail. Okay, so here's the schematic for the card. You have here the USB 3 connector that goes to one input of the analog mux. The other thing here is the PCIe edge slot, the card edge, that also goes to the gigabit analog switches. And then you have a tiny bit of circuitry here that we'll look into later. And then here you have the redriver, and then that goes to this, which is the SFP cage, where you will find the SFP module. There is really not much to this. All of this, it's just like option switches to strap some options on the redriver or on the SFP. This is all power supply and decoupling, and then some control signal that are exposed on header, which are really just for debug, are not really needed. Here, there is one thing which is provided, which is a 100 megahertz oscillator. As I mentioned in the introduction, I'm not transporting the reference clock over the optical link. So on the device side of the link, I need to recreate a reference clock, and I'm just doing this with a simple 100 megahertz oscillator and then some adaptation of the signal level to fit it to the card. And then there is this little bit of circuitry here. Now, it just so happened that the redriver that I'm using is SN75 LVP802. It's not specifically a PCIe redriver, but PCIe is a supported application for it. And because it's not specifically designed for it, it also has the same problem, which it's not detected as a valid linked partner, for the PCIe receiver detection issue I mentioned earlier. And the way they deal with that is basically by using these resistors to ground, which will provide sufficient value. There are 330 is sufficiently high that it's not going to screw up the signal too much or attenuate it too much, but it will be enough to be detected as a valid link partner. And the values are taken from the datasheet of the SN75 LVP 802. I did add this, which is just NMOS, which allows me to basically turn on and off the termination. It was just for testing. I also tested to directly short them to ground in case this wasn't working, but this seems to work fine. And so that's one of the way we can work around PCIe receiver detection issue, is to basically manually tweak the termination. I will probably try at some point with a different redriver, which is PCIe compliant and includes proper termination internally, so that you don't need such tricks. That is on the to-do list. I already have the chip picked, and I actually already have the samples. I just need to make the PCB. Something else you might have noticed is that if you look at the board, the USB 3 connector is populated on the back side of the board instead of the front side, and that's because, despite what the notes say here, I somehow screwed up and I swapped ARIX and TICs. And the easiest way to fix that was actually to mount the connector on the back side of the board, because that ends up swapping TICs and ARIX. It does swap the polarity as well, but it doesn't matter for PCI Express. PCI Express is independent on the polarity of the serial link, and it also swaps the polarity of the clock, which again doesn't matter whatsoever. And it also swaps, like, they're abusing VBus and ground wires of the USB 2 part of the USB 3 connector for control signal, wake, and reset. So it does swap those as well. But I'm just connecting those two headers, so I just had to relabel some headers. Not a problem. That's one of the reasons that I haven't actually published this card yet. I will publish the next version because I want a version that doesn't have traps on it, basically. Okay, so now that we've looked at the card, we're gonna try to see it in action. So let's first try to boot the i5 without anything connected. So the various red and black wire that are going everywhere, they're just power supply going to power supply just off screen. I'm just gonna start the 5-volt supply to the Raspberry Pi. You can't see it, but there is a red LED that started, and I need to press the power button to actually start the Raspberry Pi. I'm gonna quickly show off the configuration. So boot firmware, I think config. Yes. So here I have the PCI Express config. The only part that are enabled, I'm currently limiting myself to Gen 1. This whole setup works for Gen 2, but for some later experiments, I'm currently using Gen 1, but this setup works with Gen 2 as well. It doesn't work for Gen 3. As I mentioned in the intro, there is some equalization thing to deal with, and we'll talk about that later. And I've also disabled L0S, which is one of the low power state. The other option are not actually necessary. They're for some other cards that I'm not concerned with here. Obviously, nothing is plugged, so if I do a LSPCI, we don't see anything. One thing to note, though, if we look in dmessage, let me see if I can find it. So here you can see that it scans the external port and it sees link down, and so it removes it. But somewhere else, it gives the status, and yeah, here. And you can see there is a exclamation point and that SSC, and that's because the Raspberry Pi 5 by default has spread spectrum clocking disabled. So among the three problems that I mentioned in the intro, spread spectrum clocking is disabled because it's not active in the Raspberry Pi 5, and um, receiver detection is walked around with the couple of resistors and capacitors that are added to the data traces. And well, we're running at Gen 1, so there is no equalization. So this setup should work. So I'm going to turn off the Raspberry Pi because I need to plug the board. So I'm waiting for it to power off. It's off. I can shut down the power, and then I will plug this thing in here. Okay. I know I need to provide power to both of those. This card draws power from the PCIe slot normally, but of course here it's not plugged into anything, so I need to provide it with 5 volts. And this breakout also needs 12 volt, and it will internally convert the 12 volt to 3.3 volt and send that to the card along with the 12 volt. I think that card actually only needs 12 volt. So let me turn that on. The 5 volt is on, and then the 12 volt for this card. And this card will already start. And so now I can provide 5 volt to the Raspberry Pi again. It's still off because I need to press the power button, but let's press the power button. It's now booting. So let's see when it comes online. Okay, I can ping it, so I can SSH. And if we do LSPCI, we see our Blackmagic designed decklink quad-link recorder connected through the fiber link to the Raspberry Pi 5. And I can do, let me do LSPCI, and I want the detail on that slot. I want all the details. Let me zoom on this. And we can see that the link status is currently 2.5 giga transfer per second, which is Gen 1 with by 1. This card is capable of Gen 3 by 4, I think, something like that. And you can see here, or by 8 actually. So you see like the link capability is 8 giga transfer per second with by 8, and it's downgraded because of obviously I'm only carrying one lane here. And you can see that this is really working over the optical link, because if I unconnect the SFP and I try to do LSPCI again, yeah, it doesn't work. It can't reach it, and it throws an error. I'm just going to reconnect the SFP. And it works again. It retrains automatically, which is pretty nice. So yeah, getting PCIe, Gen 1 or Gen 2 working is really not a big deal. Actually, like I can, if let's do this. Let me reconfigure it at Gen 2. I need to wait for it to reboot. But Gen 2 should work just fine. There is really not much difference between Gen 1 and Gen 2. Okay, it's up. I can SSH to it. we still see the card. And if I do LSPCI and I ask for the details, I should see that no, my link status is 5 giga transfer per second instead of 2.5. Of course, here I'm just trying enumeration. I'm not actually talking to the card or anything, like doing anything, but it does talk to the card. It does issue configuration requests. I don't actually have drivers for this card that runs on the Raspberry Pi 5. I honestly tried looking into it, but that was just a kind of a mess. I wish I had some device I can easily plug in here, like an NVMe or something, but I don't. So I'm just testing with this card. I did actually load a custom bitstream on this card and ran a DMA benchmark test, and I can reach like 3 point useful traffic 3.5 or 3.6, I think, gigabits per second using the Lytix DMA driver and gateway. And that's basically the same number that I'm reaching if I plug directly this card in the Raspberry Pi 5. There is no difference whatsoever. Okay, so I mean, I find this already pretty cool, and that can definitely have some application already. I could actually deploy that already by just using a by one link, but I want to do further tests to get faster links up. But this brings me to sort of the first side quest of this project, because I now have an optical link over fiber. And it just so happens I also have a few of these things. And these things are optical splitters. This one is meant for, I think, 1310 nanometer. It doesn't actually say on it. But so what this does is you take a signal on the input. So on this fiber, you send a signal, and this will split it in two outputs, sending the same signal on both. Obviously, the signal is going to be attenuated. It actually does say here that the signal is split 50-50, which means that you will get an attenuation. I think that's just what the second number means here, is that you end up with, well, at least, I mean, more than 3 dB attenuation. I think probably 6 dB attenuation or something like that. Honestly, I don't remember the exact spec. I have them somewhere. And this one is an FBT splitter. I also have a different type of splitter called PLC splitter, but it basically does the same thing. So I've got several of these. And so one thing we can do is, instead of sending the signal directly there, we could take the signal that's sent by the Raspberry Pi, split it, send one half to the actual device, and then send the other half to another SFP that's going to convert it to electrical, and I can put that SFP in a random FPGA dev board and capture whatever is at the output. And that basically creates a PCI Express analyzer. And it's kind of convenient because I don't have to deal with splitting a high-speed gigabit signal electrically. And that also allows me, honestly, to have the device further away from what I'm testing, basically, because just due to the layout of things, the place where I want to capture the signal is actually at somewhat at the other end of my bench, and routing, electrical signal over long distance, especially after you split them, it could mess with the link or something like that. That's not good. And so we're gonna try that now. I need to reconfigure things a little bit, because here I have a duplex LC and I need a simplex one, so I can plug one end in the splitter and the other hand just directly. You could obviously put a splitter in the other direction as well. I actually have two splitters, but it just so happened that the development board that I'm currently using only has one SFP slot, so I can only put one SFP module to listen on one side of the link. Let me just reconfigure things. Okay, so here is the modified setup. You can see that I placed the splitter here. So what I did is that the transmit side of that module is going into this fiber, which is the input to the splitter. The output of the splitter is going to here, the receive side of this module. And the other output is going here, and it's coupled to a fiber here that's going off to an FPGA card, which has an SFP module and a PCIe slot. Now, that's a card I use for work, so it's like in a work setup. I can't really show that on camera, but it's really just a Xilinx UltraScale with an SFP and PCIe interface, so I can take whatever comes on the SFP and dump it into the um, PCI and just record it on disk, basically. I will show off the gateway that I wrote for it, the slight, the small LightX module. It's really simple. Of course, the other side of the link needs to be wired as well, and so this is this simplex fiber, which takes the transmit side of this and going to the receive side of that module. Now, as I mentioned before, I'd like to expand this setup to be able to record both sides at once. And what I've done is I actually ordered a board from eBay. At the moment, you can buy on eBay some Alibaba accelerator card. I think they were used in data center or something, and they're not useful anymore. So just getting rid of them. So they're really cheap, and they have a PCIe interface, Xilinx UltraScale, and 2 SFP slots. And so that's going to be perfect for this setup. I've ordered it. It will take some time to get here, probably like a month to get here, but I will obviously redo this setup with that board, and at that point, I'll be able to publish the files for people to reproduce this setup on their own hardware without depending on some unobtainium card. Something else I might try is some cards that you can find for cheap. They don't have 2 SFP, but they do have 1 QSFP. And you can't just take a QSFP LR4 module and then feed multiple fibers into it, because they use wavelength multiplexing. But there is something called QSFP PLR4, which is parallel LR4, which is splittable into multiple fibers. So those QSFP, instead of having a single LC duplex connector, they actually have a MPO connector, and those have 8 fibers, so like 4 pairs, and you can actually take those 4 pairs and connect them to 4 LR10 modules. So that should allow me also to dump multiple channels at once, and using as boards that only have a single QSFP, because on AliExpress you can find some development board that have 1 QSFP slot, for instance. So I bought some of those modules as well as the various optical cable needed to break them out, because you need a MPO to quad LC breakout cable. I ordered some of those. Again, they will take some time to wrap. Those are the main ways I'm planning on support both being able to publish bitstream that people can use, and with development board that they can find. Anyway, let's focus now on this setup and try it out. Everything is wired the same way. The Raspberry Pi 5 is booted, and you can see it here. If I do LSPCI, yes, I do see the Blackmagic card. Now I want to generate some traffic. As I said, I can generate some traffic when you do LSPCI. You can actually generate some traffic, but it's very low. But I quickly threw together a very small program which maps one of the memory zone of that card, one of the bar, and continuously generates a write and generates a read out of it, and does that in a loop for like 2 million iteration or something. And so I'm just gonna run that while I'm doing the capture. So this is what I'm doing here. If I run test here, this will generate some traffic. Now here on this shell, I have the the machine which has the FPGA board that's actually going to dump the PCIe traffic. And up example is the example that I wrote. This will literally just take the like PCIe traffic that's received on the SFP and write it to disk, doing no special processing or anything. So I'm going to start both of those at the same time. So I can write this, and then I can start this. Oops. Yeah, okay. So small problem, trap for young players here is that this doesn't work. It throws a bunch of error, and that is because currently if you do LSPCI, look, if I do LSPCI here, or of the cards, um, and you will see that this has one bar, region 0 memory dynamic system, but it says disabled. That's because currently there is no device driver associated with that, and so the kernel actually has disabled, which means that my little program here cannot talk to it. So what I need to do is to manually enable it, and so I'm going to do that by doing to sys device PCI, no, sys device bus, no, sys, I forgot about the bus PCI devices 00101 here, and if I do cat enable, it's currently 0, and I can do cat 1 to enable, and that will force enable it, and you will see that in the message that no, the device is enabled. And if I redo my LSPCI, let me LSPCI, I just want to see that slot, and if we look at the bar again here, no, the region 0, it doesn't say disabled anymore, so it's enabled. So now I can run my little program. So let's rerun that again. I'm starting the capture and then rerunning the test program, and this will generate some traffic. Okay, and if I look at my thing here, it recorded like about 95 megabytes of traffic. So now we need some way of looking at that. Like you can do a xdump, of course. Now, oh, I'm going to do pipe that to less. I know that BC1C1C is a training seek. It's like a comma skip. It's called a skip order set in PCIe. So I can search for that, for instance, and I can see that I do find it. So I know my capture worked. But we can do better than this. I'm gonna copy the file to my laptop. And then I'm going to use ng-scope clients. So for those that don't know ng-scope client, you definitely need to check it out. It's a fantastic project and very, very useful for a variety of things. And one of the things I'm going to use it for now is to do like PCIe protocol analysis, basically. So I did have to write a block to import my capture file, which are in a slightly strange format because PCIe is like 8-bit, 10-bit encoded, so I needed to be able to import 8-bit, 10-bit symbol. So I did write an importer, which is this thing here, and I need to pick a file. Okay, I'm gonna import this. It does take a bit of time to process everything, but there is a lot of info. And so here I know I have my symbol imported. You can see all the symbols here, and periodically there should be a training set. I can't, yeah, maybe I can see one here. Yes, here you can see comma BC, which is like a K28.5, and then a K28.0, I think. And I know that these are control symbols. But now we can do more. If I go back to the filter graph, I have my data. I can do this, which is PCIe logical. Connect this to this filter. And then I can do the data link analysis here, and then the transport analysis, and take this, take this. Okay, if I go back to my waveform here, so at the beginning you can see it says scramble desynced. That's because PCIe link is scrambled and it resynchronized on the skip, so on the skip set, sorry. So at the beginning is desynced, but here it finds the skip sets, and then it can see that it's a logical idle, and then it will start the actual decoding, and we can see actual decoded transaction. And so you can see update FC. So there is a way to get like a list view. I have to remember, how do you do that? No, not this. Analyzer, PCIe transports, and I want to, let's see, attach it here. And analyzer data link. Okay, so strangely, my transport didn't actually capture anything, which I find a bit strange. I must have screwed up the capture, and I think my test program must not have been running. So let me redo a capture. Okay, so no, it did reload the file, and you can see that in that capture I have traffic. You can see here memory write, memory read, memory write, memory read. Like I can zoom onto one of them, um, and you will see the different field bake parsed, and you can see that it's always reading and writing at the same address, because yeah, that's what I'm doing. I'm just reading and writing to the same address, and then having different data. And you can see the incrementing sequence number, and you can see the data I'm writing. It's a PRNG except for the 4 LSB, which is a counter. And so you can see 4, 5, 6, 7, 8, 9, A, B, C, D, E, F, 0. And so yeah, I think that that was pretty cool. Kind of a side quest of turning my desire for a PCI Express link into uh, you know, PCI Express analyzer, and I plan to use that for some troubleshooting. If you haven't seen my video about running a 3DFX Voodoo 2 on the Raspberry Pi 5, well, I obviously suggest that you go see that, but you'll see that I had some issues and some unexplained behavior, and so I'm hoping to use this setup to be able to see what's going on the wire and try to possibly explain some of the weirdness I was seeing with PCI to PCI Express bridges, basically. And yeah. Okay, so taking a very quick look at the gateway here, it's written in MyGen because it's meant for Lytix, and um, it's reusing the Light IC Link framework to instantiate the SerDes, GTH4 in this case. So you can see I'm just creating a stream endpoint. It's going to be the data that we send to the DMA, and then setting up the reference clock input. The board that I have has a 125 megahertz reference clock connected to the MGT. So I'm setting that up here. I'm configuring the line rate to be 2.5 gigatransfer per second. So this is PCIe Gen 1. You can set it up to 5 gigatransfer per second, but this is not automatic. Like this is very simple. It only tries one rate. So you need to know what rate your PCIe is operating at. It also means that you can't really use this to debug the initialization and link bring up, because during link bring up it will change rate and stuff like that. This isn't good for that. It only allows you to capture things once the link is up, basically. Then I'm just setting up a PLL to go from my reference frequency to my target line rate. I instantiate the SERDES using the right pins. Some configuration here, I actually had to allow to add this option to Lytix, which is align word 1, because by default it tries to automatically align to the comma symbol, like the K28.5 symbols, and it tries to align them to the MSB of the 32-bit word. So the SERDES actually will undo the 10-bit to 8-bit encoding for us and handle the alignment. But by default, it tries to put that comma symbol, which is used for alignment, in the LSB, which isn't good for PCI Express because that symbol can happen anywhere, and that was causing some bytes to get dropped because you have the regular skip set, which contains a comma symbol, K28.5, and that can happen with any kind of byte alignment. And so every time there would be such a skip set, the SERDES was realigned and drop, potentially 1 to 3 bytes to align, and that was cutting my my packets, and it took me some time to figure out what that was. The rest is just setting up some clock constraints, stuff like that. For the transmit side, I'm just transmitting dummy data. I don't really care about the transmit side, obviously. And for the receive side, what I'm doing is packing them into words of 256 bits. That's because after the 10-bit to 8-bit conversion, you obviously have data words, which is occupy 8 bits, like a standard byte, but you also have control words, and you want to know these. And so the way that works here is that I get the 8 data bits, and I also get 1 bit called control, which tells me if that byte is a control byte or was a data byte. And I need to send that to the host. I need to capture that because I will need that to do the protocol decode. And so what I'm doing is I'm inside a 256-bit word, I will pack 28 control bits and 224, which is 28 by 7 data bits. And then I'm sending that to the host, and the host will unpack those words to recreate a proper symbol that I can feed to Ngscope client, basically. Once that's done, I'm basically just passing that over to the main system clock domain, because all of that logic is operating in the recovered clock domain. So the SERDES will do CDR and create its own ERIX clock domain. I need to pass that to my main sysclock domain, which is the domain the DMA operates at. I'm using a small asynchronous FIFO and then a very large synchronous FIFO to use the ultra RAMs that are in my FPGA. And then this will end up connected to the DMA, which is the standard DMA block from Lytix, from Light PCIe, basically. That allows me to send all that data back to the host and record it to a hard drive, and then decode it with a Ngscope client. So, what are the next steps? I need to have a few test boards made. First one will be pretty simple, similar to the current one I'm using, but with a different redriver chip, the TI DS80 PCI 102. And I will also use a proper Oculink connector instead of abusing USB 3 connectors and cables. This should help with the upcoming Gen 3 experiments and maintain a way better signal integrity. The second board I need is essentially a QSFP version to extend the link to a 4x width. And check that what works with 10 gig LR transceivers also works with 40 gig LR4 transceivers and their wavelength division scheme. It should be fine, but you know what they say about theory and practice. Once those are ready, I'll be able to really dig deeper into getting the final link configuration Gen 3 by 4. This is something we'll look into in future episodes, along with using PCIe switches to overcome some of the obstacles. On the PCIe analyzer side, there are also several things pending. First thing will be to listen to both directions at once, obviously. As mentioned before, I have several pieces of hardware on the way to do that. I would also like to get this using hardware that's generally available and affordable with a gateway and software stack I can publish. That's the main goal for the Alibaba cards I ordered. I'm also planning to add a mode to the gateway where it does some of the processing on board and only dumps actual traffic and not all the idle time. This is to allow for longer captures without exploding memory requirements. Hopefully, I can fit that higher layer into ng-scope clients as a sparse waveform and drastically reduce memory usage to make longer capture realistic. So there you go. I hope that you found this interesting. If you did, thumbs up is always welcome. And if you have any comments or suggestion, leave that in the comment section below. You can also reach me on the 1bit Squared Discord. I will have a link in the description. Be sure to subscribe if you don't want to miss any future updates on this ongoing project. And you can also follow me on the Fediverse, TNT at chaos.social. I will also link them down below. That's it for today. Thanks a lot for watching if you made it this far, and I will see you in the next one. Bye.